So, as an example of using potential, suppose we have two charged plates, and these plates both contain plus capital Q and minus capital Q of charge. And what that means is there's going to be a region between the plates where there is a relatively uniform electric field. Okay. And I want to place a charge at um, one of the plates, and let's let this charge, let's let it be located at um, from here, and let's give these values some numbers. So let's let the electric field be 8.0 times 10 to the fourth newtons per coulomb. Okay. And we're going to give this charge, let's say that this is a proton. Okay. And we want to find the change in electric potential. We want to find delta V if this is a 0.5 meter gap. Okay. We want to find the change in electric potential if this is a 0.5 meter gap. So what we can do is say that, remember, the potential is equal to, or the change in potential. I really need to get in the habit of saying potential difference or change in potential, not just the potential. That's a little sloppy. There is a potential at this location, and there's a potential at this location, and moving between them gives us a potential difference. So the potential difference is going to be given by this integral E dot ds. Now, this particular case, okay, the particular case of charged plates is unique because if the electric field is relatively constant, then what that means is we can approximate that as a set number, and we can pull that out of the integral, and I'm just left with this ds, the integral of ds. But ds is the path from one plate to the other plate as the charge accelerates toward the negative plate. And we know it's going to accelerate toward the negative plate because this is a proton and this is a positive charge. So it's going to be repelled by the positive plate here. And so ds is just going, or the integral of ds, right? So ds is going to be a sliver of this. And when I integrate over the whole thing, when I integrate all my ds's, I approach the total length of the field. So what we've got then is that the change in potential is going to be negative 8.0 times 10 to the fourth newtons per coulomb. That's the field. The integral of ds is just going to be 0.5 meters because it's just the length between the two. And as a result, 0.5 times 8 is going to be 4. So my change in potential is going to be negative 4.0 times 10 to the fourth. And the units are going to be, right, well, newtons per coulomb because we have V is equal to ED, okay? Actually, we haven't derived that yet, so I won't go there just yet. We have newtons per coulomb, and from the previous slides, okay, when we were going through the initial um, um, units, we found that potential could also be written as joules per coulomb. Okay, so we can write this as joules per coulomb for the field multiplied by meters. Okay, it's either newtons per coulomb. I'm sorry, not multiplied by meters. The total unit on potential is joules per coulomb. Okay, because newtons times meters over coulombs. So our potential you can write as joules per coulomb, and we have a name for this. Okay, we have a name for this, and that name is volts. So, from a practical standpoint, this is why we are worried about what potential difference is and what it represents, because potential difference plays a role in our circuitry. It is the thing that batteries produce, and it's also the thing that our outlets produce. Okay, potential difference is the thing that our outlets produce. And it almost makes more sense from a conceptual standpoint to understand what voltage is once we talk about circuits. But we will see once we get there that voltage is the I can find the total amount of energy over a given unit of time that is supplied to a collection of charges if I know what the potential in that circuit is as the charges are flowing through the circuit. And I hope that voltage makes a little bit more sense once we get there, if it's not entirely clear what it is from here. Okay, but let me do one more example here also, and that is this. Um, if I have a positive charge, okay, if I have a positive charge, oh, there's one thing I wanted to mention. I mentioned that this is path independent. So what that means is my proton is naturally going to fall this way toward the negative plate, just in a straight line. Okay. For the same reason that if you drop a bowling ball from a ladder, it will fall on a straight line toward the ground. It won't zigzag in the air unless there's a really heavy breeze. But under the influence of gravity by itself, it will be pulled in a straight line. And so this proton likewise will be pulled in a straight line. It doesn't matter. I could force the proton to take a trajectory like this, or like this, or I could give it any path I want as long as it ends at the negative plate, then the change in potential will be the same. Okay, that's what conservative fields means, is that it is independent of path. Okay, the integral along your path is independent of the path. And it's kind of picked out from here with this cosine because the field is always going to be in this direction. So only the pieces of a path at any given point, right? If I'm moving in this direction along the path right here, only the cosine component of that is going to get picked, and that's from the dot product. And so I can have I can look at the motion at any given point along this path, and only the cosine component will get picked out. And so the result of that is when I integrate and I take the dot product between E and ds, only the cosine components between those two vectors get picked out. And so my integral along ds will just simply be the total path length between the two plates along a straight line if I can pull E out of the integral. Okay, so we have that. So what about a point charge? If I have a point charge and I want to calculate the point charge or the potential of this point charge, how do I do it? Okay. Well, let's pick some random point out here, B, and I'm going to move along a weird path to some point A. Okay. And the potential difference is going to be the difference between right. I'm going to start out at B. Actually, you know what? Let's reverse. Let's start at A and go out to B because I actually have to push the test charge out. So if I let this be some charge Q and I let this be a test charge Q naught, let's start at A and I have to push this out to B. And if that's the case, then my change in potential is going to be, it'll make a little bit more sense if we write it this way. The change in potential is going to be VB minus VA, right? If this is your initial position. And this is your final position. So with that in mind, VB minus VA is also going to equal the negative of the integral of E dot ds from A to B. Okay? But ds is just going to be the straight line distance from the charge out to this point. So you might as well, okay, because the potential around a charge is going to be the same everywhere around a circle that surrounds that charge. Okay. And the reason being, if I have a charge that's here and this distance right here is the same distance as from here to here, then I'm the same distance away from the charge and it should be exerting the exact same influence if the fields are spherically symmetric. So I might as well start here. Okay, I might as well start here. The change in potential will not be any different if I start here or here. So I can consider how much work it takes to push my charge from this point out to this point. Okay. And so we'll let this be labeled as RA, this distance, and we'll let this distance be labeled as RB. Okay. So I'm pushing the charge from A to B, right? And I might even say let's give this a negative sign so that I'm actually doing the pushing. Okay. So what is the change in potential in moving a charge from location A to location B? Delta V is going to equal negative the integral of the electric field times ds, but if we're just moving radially away from the charge, from the large charge, then ds is going to be nothing more than dr. Okay, I have an integration along a radial direction. And E, if you recall, for a point charge is given as K times Q over R squared. So this is going to be K Q over R squared. And technically, this is going to be R hat dotted into dr. And dr is going to equal the unit or the total value of my dr, the infinitesimal value, times its unit vector, r hat. So my unit vectors are going to cancel out, or they're not going to cancel out, they're going to dot to 1, right? Because this is a scalar and this is a scalar, and only my dot products are taking part in the dot product. So they go to 1. And so I'm left with negative KEQ integral from A to B of 1 over R squared dr. And the integral of 1 over R squared is 1 over R. So we have this. Ooh. Okay. And we've got negative KEQ 1 over RB minus 1 over R 1 over RA. And I need to include this minus sign. And so give me just a second here. Oh. No. That minus sign went away. That minus sign went away from the integration. That was what I was missing. The integral of 1 over R squared is minus 1 over R. And so that minus sign cancels with that minus sign. And we get this. And so what we can say is that our change in potential is going to be KEQ. Now, you can't just write this down as RB minus RA. Okay, you can't do that. To do that, we would be assuming that both of these denominators would be RB minus RA. That's not an appropriate thing to do. So, what is the interpretation of this? Well, first of all, note that this is negative. This is a negative quantity, right? And how do we know that this is a negative quantity? Because RB is smaller than RA, or 1 over RB is smaller than 1 over RA. So I can rewrite this as negative KEQ times 1 over RA minus 1 over RB. Oof. Right? Okay, so we've got 1 over RA minus 1 over RB. And what you can do now is imagine what will happen as I stretch this out further and further and further, all the way to the point where B is equal to infinity. Okay? And 1 over infinity is effectively 0. This goes to 0. So what this is telling you, okay, what this is telling you is that, and we already derived this result, KQ over R or KQ over S, right? We already have that result. That result is right. Was it on this slide? No, it would have been on this slide. Yeah, it's this result. So the magnitude of the potential difference, or the magnitude of the potential at a given point, rather, is equal to KQ over S. Okay, and so what this is telling you is this gives you an explicit formula for both the value of the potential at a point away from a point particle, and it gives you the potential difference, or it gives you the amount of work that it would take to push a charge from this point to this point. Okay? Because work is potential times charge. So if I know how much charge is on my test charge, if I know my test charge Q, and I start out at infinity and push it against the field lines to this point A, then this is the amount of work, the absolute value of this would be the amount of work that was required. Okay? So the negative sign here is coming from the fact, it's coming from the difference between starting out at infinity and pushing it in and doing positive work, or letting the field do negative work, just the same way that gravity does negative work when it pulls things down. So that's where this negative sign is coming from. But that is how you find the potential of a point charge. Okay, it's just KQ over R. Now, a couple of things. We're not going to do explicit examples of this here, but if I have, well, we'll do this example. We won't do sophisticated examples, but we'll do this example. If I have an axis, and let's say I have a positive charge here and a negative charge here, and both these charges are a distance a away from the axis, okay? And I want to calculate what the potential is at this point, P, along the y-axis, okay? So the potential of 2-point charges, or the potential of a point charge, let's label this as Q1. This is labeled as Q2. And so the total potential is going to be the potential from Q1 plus the potential from Q2. This is just straight up addition, okay? But we don't need to fuss with components, which is really, really, really nice. And so let's suppose that this is a distance B above the axis, okay? Well, V1 is going to equal K Q, let's go Q1, KQ1 over let's make that a little bit better. This is R1. This is R2. And R1 and R2 I did it again. I keep writing capital Q's. Q2 over R2. But R1 is equal to the square root of A squared plus B squared. And this also equals R2. Okay. So now charge is important. Okay. When you push along a field toward a positive charge, you're doing positive work. So we consider the amount of potential, okay? We consider the amount of potential around a positive charge as a positive quantity, right? But if you have a positive test charge in the vicinity of a negative charge, it will fall along those, and your change in potential will be negative. So pushing charges, test charges, toward field emitting regions is going to be positive or negative based on whether the field emitting region is from a positive charge or a negative charge. And so signs are important here. So what that means is that I can write this down as KQ1 over R1 minus KQ2 over R2 because Q2 is negative. Okay? So now, because R1 and R2 are the same thing, we might as well just call this R. So I can drop these subscripts in the equation, and you'll note that the total potential is just K over R times Q1 minus Q2. Okay? In the special case where the charges are the same, then along the axis that bisects two charges, one positive and one negative, the potential is not going to exist. It's going to be zero here. It's going to be zero here. One thing to note from which slide was it on? It was from here. Okay, so we have, oops. I missed it. Here we go. Yeah, I apologize. That was a long way to get here. Remember that we argued that the absolute value of the change in potential is equal to E dot ds integral. Okay, but if I take away those absolute values, then this becomes negative, and therefore E is actually equal to the negative derivative of potential with respect to position. In higher level calculus, you'll find that this is termed a gradient. Okay, this is termed a gradient. And what that means is that there's a slope that correlates with the value of the potential. And that potential, the slope of that potential, is the negative of the electric field. Or another way of saying it is the electric field is the negative of the slope of the potential. So what that means is if I want to look at along this x-axis here, the electric field, we know, is going to point from the positive charge to the negative charge. Off the axis, it's going to do this kind of thing. but along the axis, it's going to point toward there. The potential is the negative gradient of that. So what that means is that the potential will be negative on this side, and it will be very largely negative. So you'll have large minus signs, but as you grow toward the positive charge, the negative values get smaller, and when you cross the axis, it's zero, and then it grows positively on the other side um, until you reach the charge. And so, in this particular case, along the axis, the potential is going to a first approximation, be a linear line. Okay. So that's what the gradient means. Your potential is going to grow in the opposite direction of your electric field. Okay. Your potential is going to grow in the opposite direction of your electric field. All right. So the next thing to look at is going to be continuous charge distributions again. And we're going to see how we can obtain the potential from those continuous charge distributions and how we can then also relate that to the electric field for the same distributions that we've already found. All right. So we will talk to you in the next lecture.